Welcome to the Blue Economy CRC webinar series for 2025. I'm Professor C.M. Wang from the University of Queensland, and I shall be facilitating this webinar. My co-facilitator is Dr. Yuno Chu, who is also from the University of Queensland. Firstly, on behalf of the Blue Economy CRC, I'd like to begin by acknowledging the traditional custodians of the various lands on which we work today and the Aboriginal and Torres Straits Islander people participating in the webinar. I pay my respects to elders, past and present. Now, the Blue Economy CRC was established to undertake industry-focused research and training to support the growth of the blue economy, with a focus on offshore aquaculture and renewable energy production. And with now 43 participants from Australia and around the globe, the purpose of the Blue Economy CRC is to perform world-class, collaborative, industry-focused research and training that underpins the growth of the blue economy through increased offshore sustainable aquaculture and renewable energy production. Our vision is to make Australia's blue economy industries in offshore sustainable seafood and co-located renewable energy to be very globally competitive. Now, today's webinar is about the Blue Economy Symposium that was recently held in the 2025 OMAE conference in Vancouver. For over 4 decades, the OMAE conference has been the premier annual event to showcase leading-edge innovations and technological achievements in offshore engineering. Held within OMAE, the Blue Economy Symposium focused on the sustainable use of ocean resources for economic development, often featuring research and discussions on topics such as aquaculture, renewable energy, and offshore technology. Now, this webinar will highlight the presentations, about 5 presentations from the Blue Economy Symposium event, providing an opportunity to hear high-quality research and gain insights from industry leaders on the current and future directions of the blue economy. So please welcome our 5 guest speakers who will be presenting for us today. The first speaker is Associate Professor Ziyun Tay, an Associate Professor in the Engineering Cluster at the Singapore Institute of Technology. Our second speaker will be Thomas Johansson, co-CEO at Ocean Oasis AS and Senior Principal Specialist at DNV. The third speaker will be Associate Professor Peggy Chen, who is the Director of Center for Maritime and Logistic Management, Australian Maritime College, University of Tasmania. Fourth will be Per Ariel Allant, who is the Business Development Manager of the Ocean Space segment in DNV, Norway. And our last speaker will be Dr. Yana Ozagawa, who is a Senior Lecturer at the University of Western Australia, as well as the Deputy Leader of the Renewable Energy Program of the Blue Economy CRC. Now, the Q&A will follow after all these 5 presentations. So please place your questions in the Q&A box at the bottom of your screen. You can also update any questions that you wish to be answered so that the popular votes get prioritized to the top of the list. All right, so without further ado, I will hand over to our first presenter, Associate Professor Tay, who will talk on step type floating breakwater. Ziyun, the microphone is yours.
All right.
You can share your screen.
Yeah, try. No. Okay, can you see my screen now?
Yes, okay.
All right.
Go ahead,
Okay,
please.
thank you, Prof. Wang, for the introductions. Okay, good morning and good afternoon, everyone. I'm Jiong from the Singapore Institute of Technology, and I'm happy here today to present a paper that we presented in the OMAE 2025 entitled The Performance and Wave Attenuations of Step-Type Floating Breakwater Under Influence of Mooring Stiffness for Tropical Climate. So these shall be the contents that I'll be presenting today. So as a background, Singapore is one of the many cities or countries that are vulnerable to the extreme floodings as sea level rise. And Singapore often experiences flash floods due to the extreme weather conditions such as storm surges or even rise of seawater level. So there's been report of the increase in the number of floods per year. And as a result, Singapore government has allocated $100 billion dedicated to adapt the Singapore infrastructures to the rising water levels over the next 100 years. So this shows the importance of the coastal protections, and this map here shows the map of Singapore in the 1950s. So back then, we still have a lot of vegetation, such as mangroves, which are important nature-based solutions to protect the shore against extreme weather conditions. So due to the urbanizations and need for more lands, land reclamation has been carried out in Singapore, and this red pages shows the land that has been reclaimed. And as a result, the numbers of mangroves as well as the vegetation has also reduced. And coming forward in the future, there'll be more reclaimed land. So if you look at the types of distributions of grey infrastructures around the shore of Singapore, most of them are of seawalls, geotextiles, or breakwater. So even for the future, where we are going to protect the East Coast against the rise of seawater level, the bottom-founded land reclamation solution is sought in order to protect this area from the rise of seawater level. So the question is then to ask is, are there any other methods besides fixed grey infrastructures that can be used instead of these fixed structures or bottom-founded structures? So this project is a collaborations with NUS and NTU. It's entitled the Smart and Multifunctional Floating Structures for Coastal Protections and Flood Control. So in this project, we're proposing a floating breakwater that is multi-purpose, and this can be integrated with marine renewable energy, such as wave energy converters and tidal energy, to tap on this energy resource to generate electricity. So floating breakwater and marine energy converters, these are not new. There have been existing solutions in Singapore as well as around the world. For example, in Monaco, there is this floating breakwater, as well in Sweden, breakwater to protect the marinas from extreme weather. And one of the popular wave energy project is this eco wave project, where they integrate a point absorber arrays into the breakwater. So the novelty lies in producing a cost-effective floating breakwaters in relatively deep waters, and this will be tailored to the Singapore context in order to cater for the Singapore weather, as well as multifunctional with green energy harvestings in the future application. All right, and some of the possible deployment site, for example, in the southern of Singapore, the southern island, where we have good tidal energy resource, and this can be used also to create sheltered area for industries such as aquaculture, or even to create a more sheltered area for marine electrifications, such as charging stations for tugboat. So the novelty is to create a cost-effective floating breakwater in a relative deep waters and tailored for Singapore context. So two types of concept solutions are proposed here. One is a fully floating breakwaters, where they are used for deep or intermediate water depth. And the second one would be a breakwater that is integrated to dikes or seawall. So in the event of rise of seawater level, the existing floating breakwater can still be used. Only the dikes and seawalls need to be retrofitted for designs of a higher mean seawater level. So we consider 6 different types of geometry for the floating breakwater: the box type, step type, and also the pontoon, the dual box, as well as dual box with plates, and the T-shaped breakwater. So we use the CFD simulations with ANSYS Fluent to obtain the wave elevations upstream and downstream of this breakwater. And the water depth is considered 10 meters. Wave height is 2 meters, which is a common wave height that we considered in Singapore. And 3 wave periods are considered, which are the 4 seconds, 5 seconds, and 6 seconds. So this is a result that we had published in the World Conference on Floating Solutions back in 2024 in Hong Kong. So here we consider the two best geometry to attenuate the wave force, which are the pontoon type on the top as well as the step floating breakwater at the bottom. So here you can see that the step breakwater is more effective as compared to the pontoon type. And in terms of the motion, the heave response of the step floating breakwater is smaller as compared to the pontoon floating breakwater. But the pitch response of the step floating breakwater is greater than the pontoon floating breakwater. So again, this shows the wave elevations generated around the floating breakwater, and the step floating breakwater is proven to be a better solution as compared to the pontoon in terms of attenuating the wave force. So then, we know that in order to produce a better design for the step floating breakwater, we need to constrain the pitching motion of the step floating breakwater. And because this pitching motion will generate more waves downstream the floating breakwater. So the research questions will then be to ask what are the suitable types of mooring system that could minimize the motion of the floating breakwater and at the same time effectively attenuate the wave force. So here the objective is to evaluate the influence of mooring stiffness on the motion as well as the wave attenuation, to identify the optimal mooring configurations as well as to enhance the overall design efficiency of the floating breakwater. And here we show four different types of configuration. The first one is a step floating breakwater without mooring, abbreviated as SFB. The second one is the tension tendons, TT, the taut mooring, TM, as well as the catenary mooring, CM. So here we are considering regular and irregular waves, and the goal is to identify the most effective mooring configurations that enhance the wave attenuations and motion stability. In terms of the methodology, we're assuming a linear potential theory, where the fluid is assumed to be incompressible and viscous and the flow is rotational. And we use the boundary element method to obtain the motion as well as the wave elevation surrounding the structures. So this is the usual equations of motion where we can obtain the radiated damping as well as the added mass. And the free surface elevations can be computed by using this equation. For the irregular waves, you're assuming the Pearson-Moskowitz spectrum to generate the irregular waves. And in terms of irregular waves analysis, we'll be using these common formulations to obtain the significant response of the structures as well as the wave elevation. So now comes the result and discussion part. So first of all, I'll be presenting the regular waves. So this shows the hydrodynamic diffractions analysis of the step floating breakwater configurations. So for the unmoored step floating breakwater, the first natural period is around 4.1 seconds, and the second natural period is about 6 seconds. If we compare with the catenary mooring, the catenary mooring step floating breakwater shows a significant lower heave response as compared to the unmoored step floating breakwater. And it also has a lower second resonance wave period as compared to the unmoored version. This is because of the increase in the stiffness that will increase the resonance period. And then for the tendon tension, there is an negligible heave response observed for both tendon tension and taut mooring configuration. And this shows the pitch response of the floating breakwater, the step floating breakwater, where we see that there's negligible pitch response for the tendon tension as well as the taut mooring. As for the catenary mooring, there is a moderate mooring stiffness. It is observed that moderate mooring stiffness still significantly reduce the pitch as compared to the step floating mooring. So this shows the surface elevation surrounding the breakwater. The waves come from the south to the north, and the red contour shows a higher wave elevations. And here we can see that for the unmoored step floating breakwater, the highest transmissions occurs due to the large heave and pitch response. And for the tendon tensions and the taut mooring, the best attenuations occurs when the wave periods or the wavelength is short. And for the catenary mooring, moderate attenuation is observed, and it becomes less effective when the wave period is high. So next, I'll be presenting the irregular waves results. So this shows that the step floating mooring without self-floating breakwater without a mooring shows the highest motion responses, followed by the catenary mooring. And the tendon tension and as well as the taut mooring shows significant reduced heave and pitch, with the tendon tension being a better solution. So we also observed that for the heave response, the peak occurs at the natural periods around 5.5 to 6.5 seconds. And for the pitch, it's about the same as well. And from the design insight, we can show that in order to avoid resonance and shift the natural period away from the tropical wave range, then we can increase or add some heave plates, increase the stiffness or add some heave plates to the step floating mooring. All right, this shows the wave transmissions under irregular wave analysis. So the not floating breakwater produce higher transmitted waves downstream the floating breakwater. And the top mooring as well as the tendon mooring shows lower transmitted waves as compared to other types of mooring systems. Whereas the catenary mooring as well as the taut and tendon tension, they shows that they are less effective when the wave period or the wavelength is larger. Right, as a conclusion, it shows that the stiffness actually helps to improve the performance of the floating breakwater in terms of the motion as well as the wave attenuation, especially when the wave period is small. So here, it concludes that the mooring stiffness plays a critical role in controlling the heave and pitch motion, and the tendon taut mooring system offers a performance which is similar to the tendon tensions, but lower mooring stiffness, therefore making it more efficient and viable alternative. So in future research, we are going to consider the time domain dynamic analysis for transient and extreme response, as well as to investigate the nonlinear analysis or wave elevation. So here we have an ongoing research work on considering the different types of mooring by using CFD, and it shows that the hybrid type of tendon tensions with different types of taut as well as catenary actually helps to reduce the motion as well as the wave elevation downstream the structures. So here the cross-taut mooring system is shown to be best as compared to the other 6 types of solutions, where you can see that the motion is very, very small. And you can see also high reflected waves upstream the structures, where we can place, for example, wave energy converters in front of these structures to tap more energy, enhance the energy generations from the wave energy converters. All right, so that's all for my presentations, and I'm happy to answer any questions from the audience. Thank you.
Thank you very much, Ziyun, for a very insightful presentation of how to design effective breakwaters. I'm sure our audience will have many questions for you. So, but all questions will be taken after all the 5 presentations. So next, we please welcome our next presenter, Thomas, who will talk on pilot testing of Ocean Oasis wave power driven desalination plant. So Thomas, over to you.
Thank you very much, and good day, everyone. Thank you for letting me speak in this webinar. I'm always keen to speak about Ocean Oasis. I'll try not to bore you. Ocean Oasis is a Norwegian company developing a floating device for for desalinating water using wave power as only energy source. Today, I'll talk about our pilot testing, which we've been doing over the last 2 years. So quick background, go through the working principle of the Ocean Oasis, quick slideshow of the pilot design and construction, some results and conclusions, and to see a bit where we're going from here. So this is the Ocean Oasis desalination buoy. My background is in offshore engineering. I started when I was doing concept development for Aqua Solutions, trying to, as an exercise, basically, to try and see how we can use the experience from the Norwegian offshore sector to create a wave power device. So we need decent efficiency. We need survivability of a wave power device. With my background, I'm super skeptical about fixed installations on the seafloor. I would prefer a floating unit. And then what to use the energy for? Electricity is a challenge. Wave power is extremely variable. We decided to go for desalination of seawater. So you use the power to desalinate seawater. And this is the result: a floating buoy, a wave power device, desalinating water, leading water to shore with inexpensive hoses, the black type you see for all water transport, to an existing desalination plant on shore, providing additional water to existing desalination plants. So the working principle of wave power: instead of a fixed point on the seabed, we're using the relative motion of two large masses. One mass is the buoy itself, and the other mass, which we get for free, is the large volume of water inside a moon pool open to the area below. So if the wave frequency is between the natural frequencies in heave of the buoy and the resonance, so the moon pool, then the mass in the moon pool and the buoy will oscillate in different phases, and we can take out the energy by the relative motion between the two. The disk is not part of the physics, it's just giving us something to grab onto to get that relative motion out. So this is from a model test taken many years ago. One camera showing the buoy itself from the outside, and one camera looking down into the moon pool and the disk. You see that for moderate waves, we get quite a large relative motion. Energy is taken out here as in the pistons between the disk and the buoy. And this is a lot of force here, so you can't push these together by hand. So it's a reasonably efficient wave power device, taking around 35% of the wave energy that passes the buoy out. Now, the working principle of desalination. Desalination is energy intensive, and the energy is used to pressurize seawater, drive it past a membrane so that only fresh water leaks through. We can't pass it through because then the membrane will be full of salt. We need to pass it past the membrane. Then we get super salty water out to the right here, and we need to recover that energy because that's still high pressure coming out here. So that's the fundamentals of desalination by reverse osmosis. Here's a simplified sketch of how we do it in Ocean Oasis. So these are the pistons that takes the relative wave motion shown vertically on the previous slide. Basically double-acting cylinder pumps with check valves. So the piston moves to the right, sends pressurized water up here, sucks in low pressure pre-filtered seawater here, and vice versa. Wave motion is extremely irregular, as you all know. We need to stabilize it because the membranes are quite delicate. We use an accumulator, but if you wanted to stabilize it sufficiently with accumulators, because of the extremely irregular nature of waves, you would need far too big accumulators. So the clue of what we're doing is the power center, as we call it. It's a pump with fixed displacement going to the membrane, and a motor, hydraulic motor with fixed displacement coming from the brine on the same shaft. So one revolution of this will pump 100% water in here and take 60% in here, and the pressure will adjust to push 40% out as fresh water. If we can keep the revs of this system constant, then the pressure is completely constant in this loop, and the flow is constant. And what we do, we add a third electrical motor / generator here. which ensures that the RPM is constant, irrespective of the fluctuating pressure on the left-hand side here. So this is when the water pressure is high because of a series of big waves. We break the system with this electrical motor. If we have a series of low waves, the pressure drops. We add a bit of energy with the electrical motor to keep the RPM constant in this power center here. Then we keep a completely constant flow and constant pressure and constant water production. We have a battery and it's a hybrid system. If the waves die out completely, we can suck in water here and run this in a conventional way with this as a motor. So that's the principle of the Ocean Oasis system. Now pilot testing. We had the money to do a pilot test. We were going to test in National Park, and we got permission to test south of Oslo in the outer fjord of Oslo. This is an area I know better than my own living room. Relatively short waves, relatively low waves, and full control. This is a typical full-scale configuration for this environment. 7 meters diameter of the buoy, 8-meter draft, just over 100 tons displacement. So these are the sketches. We got a boat yard to make proper drawings to build this. Very simple catenary mooring system, and provided conservative loads for the shipyards to work with. So far so good. Then it got complicated. Two things happened. First of all, COVID struck. So within a few months, the construction cost was almost twice what it was before COVID. And the transport cost from Estonia to Norway was more than twice the cost. We couldn't afford that. We cannot go to China on our own. But of course, we trust to luck, as we always do. And it helps to have friends. So one of our main investors turned out they have used the shipyard here in China for more than 20 years. They had people in the yard doing construction follow-up, and they offered to stick Gaia on one of their vessels and let her off on the way back. So the other thing that happened was that we got an opportunity to establish a subsidiary company with offices and workshop in Gran Canaria. And that was really super for us. Gran Canaria is the main desalination hub in the European economy. And it's also our beachhead market. So we couldn't say no to that. So we moved the whole system down to Gran Canaria and decided to do the pilot testing here instead of here. It's fine, except that Gran Canaria has much longer waves, much bigger waves. And Gaia, as our pilot is called, is too small. So we did a lot of recalculations. We found that it can take it, but I lost my nerve on the mooring. I was not going to have her permanently moored in offshore Gran Canaria in those waves down here. So everything proceeded as normal, but we took her out from the port with tugs to do the main testing. So we had 30 or so trips out in open waters from the port. So that was the only change. Okay, so a bit of slideshow. This is construction in China, built in 3 parts: keel, main hull, and disc. Very good quality on the construction in the end. We're very happy with the solution we got. Nail-biting transport on the Tujuero to Gran Canaria, delivered in Las Palmas. It's a big structure, but it was possible to take it on the trucks. Assembly here in Gran Canaria and launched to sea after anti-fouling. We spent half a year getting all the equipment and pipes and hoses and stuff installed. naming ceremony with 3 of our directors. And this is Gaia in her home berth, where she's been for the last 3 years. Straight open to the south, very rarely, thankfully, waves from the south here. But it's been a real challenge to keep her close to 100 tons, close to a concrete jetty. Lots of good times, and some bad times. This is where our chief mechanic finds out he's got 15 centimeters to go after lifting the disc manually by hours. First testing on Gaia in 23 was a big milestone. And then after that, we've been testing. Instrumentation, we have motion, GPS, we have the relative position of the pumping arms. We have 5 flow meters on board, 21 pressure transducers on board. We measure freshwater quality, and we measure the voltage and current and charging state of the batteries on board. So we have 38 blocks of time series which we can analyze in stationary conditions. Some examples of time series. This is the pressure in cylinders, time series of pressure in cylinders, compared with the high pressure accumulator and low pressure accumulator. So we watched for the glitches in the check valves. They were working well. I was panicking about those before the test, but they're working well. Some glitches. We're looking at cavitation when we suck in water on the low pressure side. We do not want to go too low there. Instantaneous power in all the cylinders. And this illustrates the challenges with the wave power. One of the challenges, we need to take out 25 times the mean power in our PTO. So we really need robust PTOs in a wave power device. We did an extensive model test 2 years ago, just plotting quickly relative motion of the standard deviation of the relative motion against the actual power we get out. We have good agreement with the model test. Model testing is used to validate how much power we get out, how much power is delivered to the disk. In the pilot, we don't know the waves that well. So what we're looking for there is losses and fitness of purpose of the equipment we've chosen, and wear and tear on the systems. That's the essentials of this. So look at losses. Take the power delivered to the disk. Power is force times velocity. Power is also pressure times flow. So you compare the power delivered to the disk with the power delivered to the desalination system. We actually get more than 80% of the power and more than 70% of the volume by the theoretical motion of the cylinders actually delivered to the desalination, and that's good enough. It's better than I expected, and we're not changing our design to this is good enough. Energy consumption, if you add up, the power is also voltage times ampere. So take the voltage times ampere power delivered by the electrical system, plus the power delivered by the flow from the cylinders, and compare it with the amount of fresh water we get out. This is a time series instantaneously, all data points. So we see that when the engine spins freely, the electrical system neither provides or generates power. Then we have 2.7, 2.8 kilowatt hour per cubic meters, which is higher than I was hoping for. You look at all the blocks that we tested, and we're above 3 kilowatt hours per cubic meter on average for each block. That's more than my target was 2.5. And it turns out we used 4-inch membranes. They were running, or desalination membranes. They were running at the top of their capacity. To replace this with 8-inch membranes, and we got the target we wanted. So basically this is working. Where is a challenge? Most of the pilot is actually off the shelf equipment used with the within the intended spec. So for the desalination system, thanks to the power center, we can actually use standard off-the-shelf membranes and membrane housings, the same they use in the onshore desalination plants. The lever arms are designed for purpose, and the cylinders are operating with seawater with a different characteristic than they're designed for. So we have to really keep an eye on that. We had some wear on the bearings, on the lever arms. The end stop of the lever arm was not the best. It's taking too much. It's like a nutcracker. And the cylinders were getting some wear on the rods because it was too soft, the system here. They were bending a bit and giving a moment in the arms. So we're working on redesigning or improving the design of the lever arms. Otherwise, there was no significant wear and tear after the 100 hours we tested. So conclusions, Gaia works. She's delivering the expected volume and quality of water. The wear and tear is manageable. We need to change some systems, and we're redesigning the lever arms to make it easy to change the bearings and take them to overhaul. The same with the cylinders. Durability and cost is an issue. Our ambition is to deliver water profitably within a year or two in the next project we're doing. We recently had a 6 million grant from the European Commission, and we have an agreement with an existing desalination plant in the north of the island here, which really desperately needs to increase capacity. And we're installing 4 much larger commercial units in the Desalite project the next 5 years. We are in contact with 4 other desalination plants that really needs to expand. They are not in Gran Canaria or in the Canary Islands. 85% of the water is desalinated for domestic use. They're all under pressure to increase capacity, and they will not be allowed to use the grid more heavily. So they're quite desperate. So our first market is here. Then we are talking to Chile, to the Aegean Sea, to the southern part of Africa, to Australia, and for other purposes. So that's it. Thank you.
Thank you so much, Thomas, for sharing your innovative Gaia to all of us. We wish you all the best in your forthcoming projects, and you'll generate a lot of water for Canary Islands. Yeah, thank you so much. Yeah. Okay, so now please welcome our next presenter. We have Associate Professor Peggy Chen, who will talk about strategy for offshore wind farm construction. So, Thomas, can you stop your sharing so that yeah, can you end your sharing of your screen, and so that Peggy can take over? Thomas, can you end your sharing of your screen?
I'm trying.
Just close it. Yeah.
Stop share. Sorry.
Yeah. Okay. Peggy.
Yeah.
Yes. Okay. You can start sharing your screen. Okay. Yes, we can see your slides. Yeah.
Okay. Right. Thank you, everyone. So I think today I'm going to share our research result under the Blue Economy CRC project regarding the post-strategy analysis for offshore wind farm construction, and particularly focusing on the Bass Strait region. So this is the paper presented in the OMAE conference. As I mentioned, this is a part of the Blue Economy CRC project preconditions for the development of offshore wind energy in Australia. We are among the 4 packaging, and the package 3 about the logistics and supply chain. So we really focus on this area, and also have done some other publication. Like last year, we also present supply chain modeling published in the OMAE conference in Singapore, I reckon. And they also have a overall challenge of the Australian offshore wind development in the energy source and distribution magazine. If you are interested, you could have a look. So today's presentation really focuses on the port side. So this is based on our previous, the first phase of the research is an interview with the stakeholders, and we found out a lot of challenges. So the main focus today is import. So I will talk about some basic information and then overview all the challenges, then come to the port. And the major focus question is that because a lot of challenges focus on if a port, all the ports near this region sufficient to support the development of the offshore wind or not. So would be the one port strategy or multiple strategy work. So we are using this scientific method, doing the mathematical modeling, and to show out some outcome and to provide some insight. Then finally, I will show you the findings and conclusion. So this is currently the status of the offshore wind development in Australia, and 6 offshore wind zones have been declared. And currently in the Bass Strait region, if you look at the right-hand side, the map, you will see quite, crowded, but because that's a major, the feasibility license granted by the government. Currently, 11 feasibility license already are granted. And for the Northern Tasmania, if you look at here, this is another size of Northern Tasmania. The feasibility license is still under application. And so in total, currently, all the developers under the 11 feasibility license is about 23 gigawatts. As I mentioned earlier, we have some interview, around maybe 12 or 13 interviews with the developers, government, and also other organizations and ports, including ports. So there are different challenges, especially on ports. If you look at the challenge here, for developer, they really consider if the one port, one project, at the time is really suitable, or it has to be multiple port. From port perspective, they are worried about, okay, if the land size is sufficient and it's possible to get funding for upgrade, and will all the development will continue in. So there are a lot of concern also over there. So another concern maybe that also relevant to the port strategy is that where are the national targets for the offshore wind development in Australia? Currently, only Victorian government has a clear target, but other states do not. So that's also affect the confidence of the developer when they develop the offshore wind in Australia. So based on this, we did a survey to all the stakeholders, and we find out using the Swiss chips model, we found actually port availability is the second challenge is really they concern the most. So that's today's focus, and try to get some insight using the mathematical modeling. So before we go to the modeling, I want to show Aaron, because now Aaron really in this area. So maybe get a basic understanding of port's role in the offshore wind supply chain. So this is probably you could see the layout of the port. If we can produce components for offshore wind, then that may come from domestic manufacturing to the port. And there's a storage here, for deployment to offshore. But if we could not produce the major components, that may need to import. So port also has the function, need to accommodate all the imported component. And then also need to provide berths for all the, the different vessels, such, the OM vessel or the SOV, etc. So this is probably the overview of a port's role in the offshore wind supply chain. If I further use the animation, you will see, so port, if they import all the components and store store all the components in the pool. So for foundations, if we use jockey foundation, all this, or even the substation, they can be produced really from the manufacturer's side and then ship into the offshore side. So maybe pool do not need that. But if produced domestically, then maybe pool need to have that storage area. But anyway, if using the feeder vessel and transport all the wind turbine components to the offshore side, and then doing the installation, and the feeder vessel can go back to the pool, and then to have a next, shipment to help the installation of the offshore wind. So that's probably the very simple introduction of the pool's function in the offshore wind industry. So this slide shows you the current plan timeline for the project in the Bass Strait region. So as I mentioned, there are 11 developers. If you look at the small the map on the right-hand side, and when we look at all their plan, really you could see the possible construction period will be between 2029 to 2032. So if you find out they all start together, or maybe 4 or 5 they start during that time, the pools in that region may not be able to support. So the issue now is that which pool uses strategy, independent 1.1 project, or shared, better efficiency in terms of two function, storage, utilization, and construction timeline. Because for each developer, they want to really complete their project as soon as possible. So this is probably the research question. For 1.1 project is easy, simple. One project, just one pool to serve. But there may be some issues that, for example, more project coming in, there may be a congestion there, they need to queue. But multiple pool is that they put all the potential pools as a network, and then pulling all the storage and operational resources together and try to reduce the bottleneck. So this is the two strategy we use for analysis. If you look at this map, this is 4 pools in our research we try to analyze. Many of you may know that A, B is in Victoria, and C and D is in Tasmania. Currently, actually, publicly, the information publicly available about a renewable offshore wind terminal is A, B, C. And D actually is a potential one, but if there's a need, that can also be upgraded and to provide that. So we also consider that. And the left-hand side I mentioned is all the storage area, the terminal size that can support the offshore wind. Yeah. So this is probably the potential pools we use for the analysis. So this is a typical layout of the pool. You could see that it's a tower and a turbine, a 3-layer storage, and then also the nacelle. And this is a pre-storage area, and this is a pre-assembly area. So this is a berth for the vessel to load and also unload the components. And for this study, we assume, because it's about 2030, 2029, so we assume that time maybe the turbine size will be 18 megawatts. And so based on this, because this is very important to determine the storage area for ports, how big of the storage area they need to have or upgrade. So 18 megawatt, and this is all the information about the size, about the tower, turbine, and also nacelle. And we calculate probably for each how many turbines is required, and also how many hectares is required for each project with 2 gigawatts. So next slide, I show you our assumption about this modeling. We assume if each project has 2 gigawatts and using the 18 megawatt turbine. So probably in total, it requires the 111 turbine to be installed on that side and needed to substation. And we assumed 100% jockey foundation, considering the all the geometric issues there and also the turbine. So we assume we use jockey foundation, pin pile jockey foundation, and installation duration is 15 days per wind turbine, and substation is 30 days. So two could be 60 days. And we assume that the construction window per year is 12 months. Of course, this can be changed because the vessel needs to do some maintenance. So it may not be the whole, but we assume that it's 12 months because in the best trade from our interview or something, they all developer may assume that can be the 12 months. And we assume now it's 2 installation vessels per project and 2 feeders for that. So what we do when we calculate based on all this number, actually the total area of imports to storage for 111 turbine, the components probably maybe 47 hectares. However, we don't need that big because that's a procurement. You won't be able to procure all of them and store there. So we assume that 3 procurement equal batch a year. So that not a year, so for projects, so that probably require for 2 gigawatt project, maybe only like around 16 hectares area for ports. So we use this and to do analysis. If you use 1 pool, 1 project, it's easier because just 4. But after 5, it could be an issue. That's why we use this approach to calculate the storage requirement and port utilization ratio, and also analyze the construction time for independent or share. Then we consider, for the construction time for each project, we consider pre-assembly time, component transportation time, a round trip, and also offshore installation time. That's what we consider. So we analyze all this, and we also analyze some bottleneck and queuing delay if we use independent port service, 1 port, 1 project policy strategy. And then we compare if we use a share use strategy, what's the benefit? For example, how many days can be saving for construction? And so I try to analyze those. So this is the findings we got. For independent port strategy, if 1 port 1 project, so you will see this is all the 4 ports can support each project. And you may see these 2 ports, A and B, may have some space still, but D is smaller, that's why they are fully utilized. But the other port, they may still have space, but they could not accommodate 2 projects. Yeah, except maybe B. So, but if you, so the total, the construction day, you need to like 892 days for 4 projects. But if you want to go next 4 project, you need to another 892 days. So that becomes longer. So if we think about, we pull them all together to use a share strategy, then it becomes, the finding is like this. So if we can accommodate up to 6 projects and very good utilization of port in total, and also the construction day can be reduced to 984 days. So if I use the next slide to show the benefits, you will see for share strategy, the multiple strategy, 4 is similar, but if you go into 6 projects, you could save, 5 you save the most day, but 6 still okay because the port still not fully utilized to 100%. But if you're over that, it's overutilized, so there's a bottleneck there. So which means that we can save some days for construction. And that shows the gain, by using the share port strategy. So the conclusion of this project is that we compare the independent and the share pool strategy. And the key metrics for this comparison is the utilization of storage import and also the construction timeline. Apparently that share pool use strategy within these 4 pools, that's more efficient than the independent one, and we can serve up to 6 projects. And that's the more or less efficient, when project number exceed pool capacity. So independent is easy to coordinate, but there will be, if there's a larger scale development, and that will be the trouble. So, but I want to mention about maybe the final points that there are some limitations of our modeling. For example, I would assume the 2 vessels or 2 installation vessel and 2 feeder. I mean, we don't know if you have a 6 project commence in simultaneously, do you have so many vessels for that? So supply chain availability is maybe need to be considered, and we can do that. The second is that because the government is doing the auction, so all the commencement should be based on the result of auction. So they may not all come together, maybe 2 or 3 together or something. So there may be some commencement time will be different, and we need to adjust that maybe in future. Then also as I mentioned, the vessel, the maintenance, that may also affect the operating window. The final comment I want to make is that if government has a quite clear target, it's not only the 9 gigawatt the Victorian government has set, because if only work on that 9 gigawatt, we don't need this multiple strategy. But if we have a clear target for the government really to reach the net zero 2050, and I think the larger scale can help this multiple strategy, and pool can make decision in their investment, even to secure the funding. So this is all my presentation today, and any questions, feel free to ask. Thank you.
Thank you so much, Peggy, for opening our eyes to the fact that port capacity plays a very important role in offshore wind farm construction. Okay, so our next presenter is Per Errol Alond, and who will speak on the risk perspective for ocean aquaculture. So Per, to you, please.
Thank you very much. I am working on sharing my screen as we speak. Hopefully you can hear me, and hopefully you can see a few slides soon.
We can hear you. Yep.
Tell me when you can see the slide.
Perfect. We can
Is
see
it
the
good?
slides. Yep.
Okay, thank you very much. First of all, thanks very much for having me. Always very rewarding and interesting to take part in this Blue Economy CRC webinars and sessions that you arrange. So I'll have the pleasure of sharing a few views and reflections regarding overall risk perspective of ocean aquaculture. For convenient reasons, we use the term ocean aquaculture because then we are not only restricted to offshore far sea, open sea locations as well. Starting off with a little bit of background for you before we attend to the actual risk elements that is essential in this context. Fields of the future are blue. The demand for smart proteins from the blue field is highly surging. Just reviewing a few backgrounds and a few drivers that actually results in these risks. The thing is that very often the open sea looks like this. So we have a number of challenges when it comes to actually performing the marine operations and daily operations in this demanding environment, of course. So the result is, of course, Very often what you see now, large offshore fish farming installations that are based on advanced technology, marine technology. A few others, just use the opportunity to share a few of the other initiatives that are ongoing. Some of them are moving forward faster than others. Some of them are actually put on hold. But the Able one, Utrol Able, and the Big Dipper is actually being considered at the moment to be used in Norwegian offshore waters and related to licenses there. There is a big picture of what is called the Norlax Hydra. It doesn't look very impressive, kind of modest at the photo you see there. But the nice thing about Norlax Hydra is actually that it is materializing. And this is what 8,000 tons of engineered steel looks like in the manufacturing process. So this is a photo of this Hydra at the shipyard in Turkey around May. Now it is more approaching the finalization. Inside photo actually gives us quite a good view of the scaling here, and you can see the tiny people and this massive steel construction being manufactured. Last but not least, I just want to share with you a few of the mega trends that very much affect the risk scenario landscape that we need to relate to. Industrialization, we just saw that, a good example. Other one very significant item in this context is society at large and what kind of expectations government and consumers are putting towards fish farming and aquaculture. More specifically, authorities when it comes to fish welfare and biodiversity, social license to fish farm from society at large and the press and the consumers. And especially in Europe, we see an increasing trend from finance and banking that you need to prove and document your sustainability. Then you'll get good conditions on your financing and loans. So more or less what we just saw now, this cocktail of market demand and expectations from society and industrialization very much takes us to this 4-point list here that needs overall items, risk items, in our opinion, that needs to be attended to. The asset integrity itself, including design and fabrication of making sure, number 2, making sure that personnel safety is maintained on board, working place is safe. Number 3, marine environment, making sure that environmental impact from fish farming operations does not exceed the limits of marine environment, that the marine environment is actually able to accumulate and deal with the waste. Last but not least, of course, fish welfare throughout all phases of the breeding. So what I'll do now, I'll just flash a few slides for each of these, starting with asset integrity, and then I move on to go a little bit further in depth and share a few of the main reasoning behind this. Looking into asset integrity, this is, by the way, an installation planned to be installed outside Portugal called Coralis, with the pens in a submerged position. So if you look into this, the installation and the unit itself and the asset integrity, then we are very much on safe ground, because you can lean on on traditional engineering practice from marine offshore when it comes to mooring, stability, structural integrity, instrumentation, and so on. So we very much feel that this is something that we are able to deal with. Another aspect when it comes to asset integrity is, of course, that we need to rely on all the equipment and the systems being installed on board. And then not only systems and equipment supporting marine main function, but also maintaining fish control, making sure that no fish escapes, also monitoring and limiting waste and dispersion to the sea, maintaining ocean health, and of course fish welfare. Moving down the list, the next point you may recall was HSE, personnel safety. Here we also very much can, if relevant, we can relate to the marine codes that we know so well when it comes to fire safety, life saving, emergency evacuation, if that is necessary at the most extreme extent. Second item when it comes to personnel safety and is occupational health or occupational issues while working out there. And in Europe, we see that aquaculture workers, fish farmers, are number 2 on the list when it comes to registered issues, health and safety issues, working at their working place due to falling objects, maybe working at heights, but mostly pinching and crushing is very high on the list, unfortunately, we see. And then an important item is, of course, personnel transfer. You need to transfer personnel from one installation or one unit or vessel to another, and that is always a very risky operation. Competence, last but not least, competence in the meaning of mindset towards safety is something that needs to be attended to, and we actually need to be improved. We see very much. Third item was fish welfare. Fish welfare is mainly related to physical health of the fish, but also very much concerned is the behavioral needs of the fish. Different types of fish behaves in different ways and are more healthy and grows faster and likes it a much better when it, for example, are able to swim in circular motions and not meeting a corner. Other environmental conditions that is more moving into the area of water quality, water turbidity and salinity, temperature of water and similar. Diet, nutrition, something that we see a lot is what we refer to as a stocking density. If it's too crowded, the fish welfare index goes down, and very much crowding and transportation, fish handling in general really is reported to stress out the fish and will cause diseases, especially of the more weak parts of the fish crowd. So essentially addressing cleaning, medication, if any, and how you crowd the fish and how you monitor the health condition, continuously monitor the health condition of the fish is of the extreme importance. The last item here was ocean health, more relating to biosecurity and chemical discharge, and also nutrient discharge to the marine environment, and how this is controlled and monitored and also restricted as far as practical. more also by the benthic impact. It's very much monitored by doing benthic impact continuously, and then getting the actual status of the marine environment in the very near proximity of the fish farm. Attention, of course, from an assurance point of view is to equipment and systems installed that affects and control this emission of marine environment. And of course, part of the biosecurity item is to prevent fish escape, where you focus on the barriers and net pen, ensuring no fish escape. Monitoring and limiting pollution to water from fish waste and feed surpluses is, of course, something that we need to pay attention to. Okay, time is running when you're having fun. So my very last slide looks like this, summing up what you just saw. Usually when fish farming is discussed and risk towards fish farming is discussed, the top two is very much discussed. Partly marine environment, because you need to ensure no fish escape. But there's a lot more to it when it comes to protecting marine environment, and there's a lot more to it when it comes to fish welfare that we need to take care of. Last thing that I want to air with you is a certain different approach to the aspect of risk, where you could split it into four, where you focus on the equipment and the system put to use. You focus on the procedures on board, how is things done and what is done, and in what order is it done, and what kind of organization do you have on board, command lines and responsibility. And last but not least, of course, mentioned before, competence, which is mainly mindset and safety mindset. But I want to remind us that when you do certification and when you do verification of these segments, we focus mostly on the equipment and the systems, and you assume that the procedures and the organization and the competence is okay, that it works really well. And that is something that I think we need to bring along when we ensure safe and sustainable offshore fish farming. Thank you very much, everybody.
Thank you so much, Per, for another interesting and very, very enjoyable presentation on the risk faced in ocean aquaculture. Thank you so much. So now it comes to the last speaker. We have Dr. Yana Azagova from University of Western Australia to tell us about wave loads on offshore wind turbine monopiles. So Yana, off to you.
Excellent. Thank you very much, CM. Before I get started, are you please able to confirm whether you are able to see my screen?
Yes, I confirm.
Excellent. Thank you. All right. Well, thank you, CM, and thank you, everyone, for letting me speak to you today. So I'll be talking about wave forces on offshore wind monopile foundations. And this work comes from the Blue Economy CRC, as well as the University of Western Australia. And there were a huge number of people involved whom I'd like to acknowledge. All right, so to get us started, I mean, clearly we put offshore wind structures into quite energetic locations. We put them in places where it's windy, and because waves are generated by wind, typically these locations will also have large waves. So then in design of these structures, we need to account for the forces that the structure will experience during its lifetime. That's the thrust force from the wind, as well as forces from the waves and the current on the submerged part of the structure. And there is also excitation coming from the rotor because the turbine rotates. So all of these forces or excitation, they're actually functions of time. I mean, they vary in time, as we can see on the right-hand side. And in fact, they're oscillatory in nature. And so it's quite common to look at them in a frequency domain. So on the graph here, we've got frequency on the x-axis, and then on the y-axis, we've got effectively amplitude of the excitation across the different frequencies, but the amplitudes have just been normalized. So we can see the wind spectrum is plotted in green. We've got a typical wave spectrum plotted in blue, and then the rotor passing frequency range is shown by the sort of shaded blue area, and then the blade passing frequency range is shown by the shaded red area. So it's quite a sort of busy space. And if we think about our offshore wind structure, I mean, it's a very tall and slender structure. So it's not infinitely stiff, and in fact, it's subject, or it's subject to vibrations or sort of elastic bending. And so commonly in design, we aim to place the tower bending natural frequencies in these sort of safe zones, so that we are away from the direct excitation from wind waves and the rotor. And the most commonly targeted sort of frequency range is referred to as soft. So it typically lies between the 1p and the 3p excitation. And so, like I said, it's already a very sort of congested, busy space, and things get even worse when we also take into account nonlinear wave forces or nonlinear wave excitation. So what are nonlinear forces? So in addition to the forces at the sort of main wave frequencies, we also get excitation at frequencies above the linear waves as well as below. And so these nonlinear forces have a special structure. I mean, they follow the sort of harmonic structure. And so I'll be using numbers sort of 0, 1, 2, 3 to denote the different harmonics. So 1 just stands for the sort of standard linear wave forcing. 2 would be the second harmonic. So that those are wave forces that act at frequencies roughly double of the linear waves. So like I said, we've got these nonlinear forces that act at different frequency ranges. They also scale nonlinearly with wave amplitude, which means they become gradually more and more important in sort of severe conditions. And so, I mean, it's probably quite obvious already that they might be able to excite resonance because they span these additional frequency ranges. And in current sort of design practice, they're not particularly well accounted for. So really the aim of our work is to have a better or more detailed understanding of this sort of nonlinear loading regime, and then to be also be able to translate it into engineering models that can be used in practice. So to gain better understanding of the problem, we carried out some laboratory experiments. So here on the picture, we've got a model monopile. We've got a load cell at the top and the bottom. So we are able to measure the total horizontal force from the waves. We can also calculate the overturning moment. And we've also got wave gauges, which allow us to measure basically the waves, the wave elevation. So hopefully this video is playing, but I'm just showing you footage from one of the experiments. We've got a wave crest going past the structure, and we are measuring the forces that the structure experiences. So just to give you some background to the tests, obviously these are reduced scale tests. So our monopile was only 16 centimeters in diameter, but that corresponds to about 8-meter diameter in full scale. And the full scale water depth would have been 30 meters. Okay, so in the lab, we have a wave maker, so a machine that is able to generate waves. And we use wave groups. As an example is shown here. This is just a measurement from our lab. And the reason we'll use wave groups is because they represent realistic loading history. I mean, they are broad-banded in nature, so they contain multiple frequencies, as one would see in a sort of wave spectrum in the open ocean. And the profile of this particular wave group also corresponds to a large wave event in the open ocean. They're also short in duration, so we don't have too many reflection issues in the lab. And we use a technique. So each condition we run multiple times. So first as a sort of a condition with a large crest, and then we do the same sort of wave group, but upside down or inverted. And then we are able to, by combining these different tests, we are able to separate the total measured force into the different harmonics that I introduced earlier. And this will become quite useful. Okay, so what did we measure? I mean, this is the actual measured time history from the video that I showed you earlier. And we clearly see it's highly nonlinear, right? I mean, it almost has the sort of sawtooth profile. We can see some high frequency content as well. And if we now look at the sort of process data, I have separated out just the linear component shown in blue, as well as the second harmonic shown in yellow. And it's pretty clear that the second harmonic content is large. It's more than 40% of the linear component. So, you know, these nonlinear forces are really significant. So we can look at all the other harmonics, and we are here looking at them in the frequency domain. And in this particular test, we were able to sort of clearly separate all the way up until the seventh harmonic. So really the range of frequencies over which wave excitation acts is very, very broad. And if we sort of think back to our diagram that we had earlier with the sort of safe regions of frequencies, we clearly see that these nonlinear wave forces would overlap with the previously considered safe zones. All right, so now we have an understanding of the sort of complex loading. Our next task is to try to come up with models that are able to capture some of this nonlinearity. So the current practice for sort of monopile loads is to use something called the Morrison equation, which is a combination of inertia force as well as a drag force. And because the cylinder or the monopile is relatively slender compared to the wavelength, in fact, the fluid sort of kinematics or the fluid velocity, which I denote by U, and the fluid acceleration, which I denote by U dot, they can be taken from the undisturbed test. So they can be taken from a scenario as if the monopile basically wasn't there, just because the structure doesn't disturb the flow too much. And we also know that because the cylinder is not so slender that there is lots of flow separation. In fact, potential flow is still, or potential flow effects still sort of dominate. So the second term, this sort of Morrison drag term, it really is just a small sort of addition or small correction. Everything is dominated by the first term, the sort of fluid inertia loading. Okay, so if we go back to our measured nonlinear signal and we apply the simplest version of the Morrison equation, we get the red curve. And I mean, we get some of the time history okay, predict okay, but it's obviously not perfect. We are under predicting the peak, and we don't have any of this high frequency content. So people have thought about ways to introduce nonlinearity. So for example, we could use sort of nonlinear kinematics, so nonlinear fluid accelerations in the formula, but it does mean we would need these values everywhere in the water column, from the sort of instantaneous free surface all the way to the seabed, and that's computationally expensive to obtain. Now, another way is to try to basically transform the Morrison equation. So transform this vertical integral of the fluid acceleration. We can transfer it into a horizontal integral of just the wave elevation. And we can do a few more sort of manipulations, and we arrive at really a transformed nonlinear inertial loading, which is now expressed purely in terms of wave elevation. So we have gone from fluid acceleration needed everywhere in the fluid domain to just a point property. So all we need to know is how is the free surface moving up and down. So applying this transformed FNV model to the data that we had from the lab, we get a much better match between the experiments and the model. So we can also do comparisons sort of harmonic by harmonic, and this becomes sort of even clearer when I look at slightly more nonlinear case. So this is really getting quite violent waves near breaking, and we can see that the model agrees with the experiments really quite well up until, you know, all the way to the sixth harmonic. Here I've just highlighted sort of how large some of these nonlinear terms get in very nonlinear waves. I mean, the second harmonic is close to 60% of the linear term, third harmonic more than 20%. So neglecting these terms is really not ideal. All right, so in summary, we've looked at nonlinear wave forces on monopiles, and we've seen that they truly are a significant proportion of the total load, and therefore, are important for estimating the ultimate loads on these structures. We also have seen that they have really broad frequency range, and therefore they could excite resonance and are also important for fatigue loading, and currently are not well accounted for. But this sort of new transformed FNV model uses only wave elevation properties or wave elevation history. So it's really quite simple, has low computational costs, and therefore would be suitable for engineering practice, and has been able to capture the main nonlinear features, as we've seen in the comparison with laboratory data. We've got a few things ongoing in terms of where we would like to take this work next. But before I wrap up, I just want to mention one thing, and that's sort of the implications of this work for, I guess, for Australia. So our wave climate is quite different to the wave climate in the North Sea, where most of the offshore wind has been deployed up until now. Our waves are much longer. So on the left-hand side, we've got energy period, the sort of mean energy period. And on the exposed southwest and south coast, typical energy period 11 seconds. Maybe on the south east coast, which is more sheltered, 7 to 8 seconds. Whereas looking at the North Sea, the periods are more like 5 to 6 seconds. And the trouble is that in the sort of long wave regime, which we have in Australia, these nonlinear forces become amplified. So on the left-hand side, we've got a picture of the linear and nonlinear forces on a monopile in really long waves versus shorter waves on the right-hand side. So correctly accounting for nonlinear wave loads is particularly important in wave conditions that occur in Australian waters. So that's all I wanted to say today, and thank you very much for your attention.
Thanks, Yana. Well, all our 5 presenters are so passionate in presenting. We ran out of time for Q&A, so I will have to wrap up this thing. So first of all, I'd like to thank all the 5 presenters, and especially our audience for attending this webinar. The recording of this webinar will be made available in the coming days. So please check out the CRC events page for any upcoming webinar. By the way, your questions, if you have any for the presenters, can be sent to us, and we shall process it. I will send the questions to the respective presenters for them to answer your questions. So because of due to lack of time, we have to end our webinar now. I want to wish you all a very nice day ahead. So thank you, everyone.
Thanks and bye-bye.
Bye.